start now, but I propose that we still wait a few more minutes for other people to join. We have some time in the end still, so no hurry. Okay, maybe it's time to start. So welcome to the Future Experiments session in the DS conference. So we are three of us to chair the session. It's Markus, Salvatore, and myself. We always try to be at least two of us present in the session. Sometimes we of course will all be connected. We have two types of talks in our sessions. Some are invited talks or more larger summary talks from the larger experiments, and others are the contributed talks. They were submitted regularly to the conference. Therefore, we have two time slots assigned. So basically, the larger talks have 20 minutes speaking time and 5 minutes for discussion. The smaller or the basically contributed talks, they have 50 minutes speaking time and 3 minutes time for discussion. And we want to remind every speaker 5 minutes before the end of the speaking time to basically summarize or come to an end, such that we still have time for discussions and to talk to each other a bit. Okay, so the first talk is by Ian. It's an invited talk about breakthroughs in detector technology. And I'm very much looking forward to this talk. So Ian, it's your time now.
Thank you very much for the invitation. I will talk about breakthroughs in detector technology and how we can ensure they continue. Why? Because instrumentation is the great enabler of our science, both pure and applied, and HEC in particular. And how can we sustain it? The recent basic research needs DOE HEC detector R&D roadmap, which I have a report in detail, provides the answers. And if you like to see the most recent developments in the field, please look at the CPAD 2021 website. Over the last 125 years, through careful measurement, observation, and deduction, we have developed remarkably successful prevailing theories, the standard models of particle physics and cosmology. In the case of the former, it is highly predictive and rigorously tested in some parts to 1 part in 10 billion. Here is a list of some of the key discoveries and measurements in our field. And instrumentation was the great enabler of all of that. How do we sustain this going forward? Transformative discovery in science is driven by innovation in technology. Our boldest undertakings in particle physics have at their foundation precision instrumentation to reveal the profound connections underlying everything we see, from the smallest scales to the largest distances in the universe. To understand its fundamental constituents and to reveal what is still unknown, we must invent, develop, and deploy advanced instrumentation. The above words are the opening paragraph of the DOE Basic Research Needs for High Energy Physics Detector R&D report that was released last September. So I report on this study, and we use the word instrumentation and detector R&D interchangeably in the report. The co-chairs were Bonnie Fleming and myself. I'd like to stress from the outset, there's an incredibly strong overlap in detector technologies between high energy physics and nuclear physics, especially the JLab 12 and the Electron-Ion collider. And congratulations on the successful CD1 review. The report was produced by a remarkable set of conveners and panel members, 66 in total. Our field has made remarkable progress. The more we have learned, culminating in the triumph of the standard model, the better we have been able to delineate what we don't know. Today, most of the universe is not understood. What we know is a droplet. What we don't know is an ocean, and that ocean is for us and future generations to explore. There are mysteries everywhere, and here we name just some of them that drive our research in particle physics. To determine a path forward to address these, we need to study the universe in new ways, and these new ways require new tools. We are very much in a data-driven era. The gestation time to realize the tools and the experiments are long, 30 years or more in some cases. Accordingly, for the most ambitious experiments to take the data to answer these questions, we must develop the tools and instrumentation we need now. If history is our guide, realizing these tools will open new opportunities because new directions in science are launched by new tools much more often than they are by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of the tool-driven revolution is to discover new things that have to be explained. The challenge we are faced with inspires us and the next generation of scientists too, and you can see that inspiration in the faces of these young children. Our job is to make measurable what is not so. This report describes 4 grand challenges which are derived from the discoveries we aim to make and the technologies to enable them. They encompass broadly the overarching challenges for the technologies that we need. Advancing HeC detectors to new regimes of sensitivity, using integration to enable scalability for HeC sensors, building next generation HeC detectors with novel materials and advanced techniques, and mastering extreme environments and data rates in HeC experiments. The charge was to survey the current state of HEP technology, identify key capabilities and performance requirements, and identify technologies to provide or enhance such capabilities. To articulate priority research directions called PRDs to push well beyond the current state of the art, potentially leading to transformative technological advances with broad-ranging applicability, to flesh out required R&D efforts with deliverables, with notional timelines, and key technical milestones, and elucidate the technical infrastructure required to support these efforts. We were asked to formulate a small set of instrumentation grand challenges that could result in game-changing experimental capabilities. The charge also highlights the importance of R&D and its main goal, and I quote, "To meet this challenge, HeC aims to execute a program appropriately balanced between incremental, near-term, low-risk detector R&D and transformative, long-term, high-risk detector R&D." And this is very well aligned with the guidance from the P5 report, which along with the 5 science drivers identifies the importance of instrumentation R&D, where it calls for a balanced mix of short and long-term R&D in the current era. While this BRN does not describe the science opportunities and technologies to realize them, while it does describe them, it does not prioritize the PRDs. Finally, we strive to reach a broad audience, including the scientific community, the public, and decision makers. Science questions and the opportunities drive the next generation of experiments, and accordingly, we started with the science drivers laid out in the P5 report and created 5 science panels: Higgs, neutrinos, dark matter, cosmic acceleration, and exploring the unknown. We defined 7 technology panels: quantum sensors, solid-state calorimetry, readout and ASICs, photodetectors, noble elements, and trigger and DAC, which connect and cross-connect to the science drivers. Because of this web of interconnectivity, we benefited greatly from a cross-cutting panel that identified the synergies and holes which we could then fill throughout this process. The process began in August 2019 when we were charged by DOE. We then identified the conveners who recommended the panel members and additional members. Altogether, there were 66 panel members in total. Balance is important across many metrics. 60% of the panel was drawn from the university community, 40% from the national labs, as well as across gender. Women numbered 44% and males 56% of the panel. In the fall of 2019, the panels began regular meetings with groups, across groups, and with the community through open meetings and surveys, and drawing from the 2018 CPAD report. This led to an interim report with the first draft of the principal ideas in each area laid out leading up to December and the annual CPAD workshop. To continue to connect with the broader community, many panel members attended that workshop in Madison, with the goal to provide a community forum to communicate with the BRN panel, timed to be just before the BRN workshop in Washington, DC. The 12 plenary speakers on day one were mostly BRN panel members. Town halls provided further opportunities for dialogue. The December workshop was a combination of months of study and community input. We convened December 11 to 14 in Rockville. The plenary talks were comprehensive and inspiring, and here is Roxanne Jeanette from Harvard on the first plenary day presenting the status of Noble Elements Technology panel. The talks were streamed. Parallel sessions continued beyond this, where the panelists worked through the substance of their group, the connections between them and the first draft of the PRDs, grand challenges, and the report itself. In spring 2020 and early summer, we streamlined and refined the report and presented it to HEPAP in July 2020. It was then published in September. This study is complicated by the connection between the physics and the technologies and the cross-cutting areas between them. To capture this, we set up an interconnected structure shown pictorially here. To start, the science drivers define technical requirements to accomplish the experiments that answer the scientific questions. The PRDs then address these technical challenges. All the PRDs are encompassed by the grand challenges described earlier. The panels work to define their purview. For the physics panels, the science that drives them and the technical requirements. And for the technology panels, the PRDs that address the instrumentation needed to succeed in this program. The cross-cutters were tasked with developing the grand challenges. The cross-cutters did this by looking across physics and technologies and finding complementarities and holes and identifying ways to fill them. In this way, the grand challenges they developed encompassed the PRDs and all the work of the panel. This is shown here pictorially by the large yellow ellipse. Before we look at each of these panels' efforts, it's important to note that in order to realize these grand challenges, we must succeed in laying the right foundations. These foundations, which form an ecosystem, are people, facilities, and resources, and connections and collaborations, starting with an advanced workforce. An advanced workforce starts with people and a commitment to diversity. Excellence equates to diversity. If we are to realize the grand challenges that will enable our field to have a bright future, and these grand challenges are greater than anything we have accomplished until now, we must recognize and make a commitment to equality, diversity, and inclusion in HEP instrumentation, R&D. To accomplish the best science, we must commit as a community right now to action, to overcome the social injustices in our own backyard and realize the impact of a diverse workforce. We must find, develop, and invent new ways to attract, encourage, recruit, and support a diverse community. We must enact an inclusive environment within instrumentation and within particle physics at all levels and across the areas in which we work and that we touch, including academia, in the universities, and national laboratories, and in industry. Some small steps are being taken to draw young people from diverse backgrounds to instrumentation, outreach programs, undergrad research opportunities, and recognition through awards. But the scale of these initiatives must be dramatically increased and new initiatives developed with urgency. The technical teams building today's experiments include professional engineers, highly experienced in microelectronic design, advanced mechanical design, computing and data acquisition, as well as scientists from HEP, basic energy sciences, nuclear physics, and other STEM disciplines. To succeed in creating tools and new technologies, we need to succeed in excellence in the current and next generation of our people. A diverse pipeline, university-led partnerships, connections to other disciplines, and appropriate recognition. These experts, in turn, educate the next generation in advanced HEP instrumentation techniques and development, transforming not only HEP, but other fields too. Another essential part of the ecosystem are unique capabilities and facilities. Access to advanced microelectronic design and tools, semiconductor foundries, and so on is critical, as the use of ASICs is ubiquitous in high energy physics instrumentation. In addition, unique irradiation facilities, test beams, characterization facilities, low background or low temperature facilities are crucial for preparing and testing the detector systems we use. In this report, we make the compelling case to maintain the core facilities listed here and to develop new ones. All 5 science drivers benefit from this, as is indicated in the table. The third essential part of the ecosystem is connections beyond high energy physics. The pace of development in other fields of science and engineering is breathtaking. We can achieve so much more when we work together rather than working alone. And this is true within high energy physics and with other parts of the DOE, from nuclear physics to BESS, and with the National Science Foundation and NIST, and other federal agencies, between universities and national labs, and with commercial partners and with foundations. While collaborations can occur organically, much more can be achieved, and notably on a large scale, by establishing flexible organizational structures to bring together the community from the universities and the labs in technical areas. Models for this are the CERN R&D collaborations, and within the DOE, the National Nuclear Security Administration R&D Consortium. The HEP community has been an important contributor to broadly applicable innovation in instrumentation, from the invention of the World Wide Web to advances in MRI, PET scan as shown top right, through the development of a process to manufacture BGO crystals, and bottom left, large area hybrid pixel detectors used in medical imaging for X-ray science and much more. The instrumentation plan outlined in the BRM will lead to the development of new technologies that hold the promise to be as broadly applicable and equally transformative. So let's look at the plan, starting with the science drivers. At the energy frontier, we considered a range of possible future energy frontier colliders, both E+E-, Higgs and electroweak factories, and proton-proton colliders at energies above 100 TeV. They are both precision measurement machines and discovery machines. Understanding the enigmatic Higgs boson, including its self-coupling and possible connection to dark matter, as well as direct searches for new particles, lead to the stringent technical requirements shown here by science goal and by specific machine class, E+E- or PP, and by technology through tracking calorimetry and trigger and readout, and how these map to the priority research directions shown as the numbers in blue. Each science driver has a timeline. This is for the energy frontier. Across the top, you see the LHeC and generic different possible future high energy machines in blue, and below the PIDs color-coded by technology. The time is now to conduct the R&D to be able to begin to build detectors in the early 2030s for E+E- machines, which would be the first to come online, and later the Hadron Collider experiments and machines. In neutrinos, the experiments and technologies span a broad range in energy, in size, and technique. The questions answered in recent years have led to more questions and a push to move to the regime of high precision measurements of the neutrino mixing matrix to continue to explore the unknown territory and be prepared for surprises and new physics, as has been true in the neutrino sector in the past. The science is in the table, like in the Higgs. It motivates measurements and technical requirements which map to the PIDs shown in blue. Here is the timeline. Ongoing experiments and future ventures are summarized at the top and map out a long-range vision, with the PIDs defining the technology development programs below needed to get there. For every gram of ordinary matter in the universe, 5 more are dark. We don't know the dark quantum or quanta. Our experiments include pushing down to the neutrino floor in WIMP searches, particle-like dark matter with low masses, wave-like dark matter, and the remnants of dark matter interactions. At right are a number of tables that we have in the report summarizing this with the PIDs in blue. On the cosmic frontier, we are working to drive cosmological measurements to new spatial and temporal scales, and in doing so to explore the properties of inflation, dark energy, and dark matter. In these experiments, constraints on neutrino physics complement measurements made by terrestrial techniques. Again, you see the summarizing table at the right, and the images give you a sense of the open questions and the spatial and temporal scales of the experiments we need to address them. Explore the unknown is a little different from the other science drivers, as it covers several classes of experimental precision measurements in heavy quark and charged lepton flavor decays, searches for charged lepton flavor violation, tests of CP violation, and probes for new physics in the dark sector and for new fundamental forces. The diagram at the lower right summarizes the different channels and timescales for different observables across a range of energy scales. And on the right is an example table of which there are several that connect the science through the technical requirements to the PIDs. The 5 science drivers and their technical requirements motivate, thank you, the instrumentation needed in the 7 technology panels. For each, there are PIDs defined. Each PID is further delineated by thrusts, and for each PID and its thrust, actionable research plans are laid out. With 26 PIDs, many with multiple thrusts, we cannot go into this level of detail here, but you can find this laid out in the report. Calorimetry is defined by 3 PIDs, which encompass, broadly speaking, energy resolution, spatial, and time resolution, radiation hardness, R&D, and finally developing ultrafast media for background rejection and particle ID. And in blue, the technical requirements they address. We note the connections outside of high energy physics here, as well as the existing and needed facilities and capabilities. The needs include simulation, facilities, and people. In noble elements, 3 PIDs are defined and 2 of the cross-cutting PIDs are referenced. They include, again, broadly speaking, enhancing and enabling modalities in detection and developing new modalities, better understanding and characterization of microphysics, and advancing material purification and assay methods, and finally, addressing the challenges related to scaling these technologies to very large sizes. Again, here, we list the connections outside of HeC to nuclear physics, astro, and beyond, and the facilities, capabilities, and people needed to succeed. In photodetection, 5 PRDs are defined that focus on detection across extended wavelengths and down to single photon precision, advanced spectroscopy, precision timing, development of optical couplings, and as we see in many areas and here too, adapting the technology for extreme environments. Connections outside of HeC, including to astronomy and more broadly medical imaging, biology, and so on. Here, close connections to industry are important for fabrication and procurement, as is existing and new facilities. Quantum sensors range from qubits to technologies to NMR-based sensors and atom interferometers that provide ways to probe wave-like dark matter and to detect gravitational waves at frequencies between LIGO and LISA. The PRDs span increasing sensitivity to surpass the quantum limit, to increase sensitivity by enabling ensembles and networks of sensors, enhancing low-threshold quantum calorimeters, and also the general question of the enabling technologies quantum sensing needs. Quantum sensing is intimately related to quantum information science as well as other areas, and to advance the field, the availability of large high-field magnets and the development of inexpensive dilution refrigerators is needed. ASICs are ubiquitous, both in society and in our field. The particular challenges are encapsulated by the PRDs and are in the ability to develop ASICs to handle the extreme environments of high radiation, high data rates, and low temperatures, in the need to create building blocks of systems on a chip for these environments. This work is closely connected to instrumentation needs in basic energy sciences, NASA, and for stockpile stewardship. Foundry access is crucial. The cost is high, and there are few foundries that will engage with this work. The work is exceptionally specialized and dependent on a stable long-term workforce. Ameliorating these challenges through collaboration is part of the solution. Silicon is the primary technology for tracking the vertexing and collider physics, both at the energy frontier of heavy quark physics, and is the imager in cameras for optical astronomy. 3 PRDs aim to significantly improve resolution in space and in time, and in high-density environments, systematically exploring alternatives to silicon as the active medium, which can improve, for example, the red response for cosmological studies, and advanced materials to provide for advanced integration of sensor capabilities and to determine thermal and mechanical management solutions that will lead to minimum mass trackers. The connections outside of HeC are many and listed here. The irradiation facilities, beam test facilities, and access to ASIC design and development is critical. Our data is driven, in a data-driven era, we are characterized in part by the large volumes of data and the very high rates at which it must be analyzed in real time, continuously, and in the transmission of that data if we are to reach the exascale. That would be needed, for example, at future high-energy PP colliders. There is a need to develop technologies for autonomous detector systems and timing with picosecond synchronization for large astronomical arrays of detectors. The connections are very broad across the Office of Science, and with industry again, access to ASIC design is critical, and to irradiation facilities. And finally, in summary, all 26 PRDs, including those that are cross-cutting, PRDs 24 manipulate detector media to enhance the physics reach, 25 to advance material purification and assay methods, and 26 to address challenges in scaling. For all 26 PRDs, you can see each of their connections to the 4 grand challenges on this slide. Now, I should say that micropattern gas detectors were not in this BRN scope, but are a very important technology. For the current status of this technology, see Maxim Tito's talk at CPAD 2021, including applications to JLab 12GeV and the Electron-Ion Collider, where all proposed detector concepts have large area micropattern gas detectors. Applications include tracking, PID-rich, and TRDs. If you would like to get a bigger summary of what I've just said in more detail, please look at the recordings of the 9 summary talks by the 7 BRE technology panels, the micropattern group, and the low background, low threshold group for the many exciting instrumentation results, and also see the slides of the 5 science driver talks on day 1 at this workshop, CPAD 2021. Now, with the BRN well underway, SNOMAS was launched, and that will be followed by a new P5. We encourage the community to build on the research plans presented in this report and to refine them further and continue to introduce and develop new instrumentation ideas during SNOMAS 2021-2022. The European strategy update states that the community should define a global detector R&D roadmap that should be used to support proposals at the European and national levels. We support the stance of the ESU articulated towards instrumentation, we encourage the US particle physics community through the SNOMAS process to play a role in the ECFA Detector R&D roadmap, which is set in a global context. And after SNOMAS, CPAD should continue to play a role in developing this international roadmap and can be the vehicle for the realization of the program outlined in this report. Now, BRNs have impact. The recent microelectronics BRN has led to a joint DOE National Lab program announcement on the 24th of March, a multidisciplinary co-design approaches to basic research that could enable transformative innovation in microelectronic technologies for sensing, communication, and computing. And as a result of this BRN, it was seen on April the 1st with the announcement of the Instrumentation Traineeships Funding Opportunity announcement to support graduate student training in the areas of sensors, front-end electronics and data acquisition, and system design and engineering as well, with £5 million been made available. $5 million, I should say. More generally, the report has been influential in the office. We believe we can do more. We are preparing a BRN brochure. We will organize a community letter writing campaign, and we'll work with the Fermilab UEC to carry the report message to Washington, DC. The 66 panel members acknowledge the many people who contributed at various stages of the BRN study beyond the report. The 142 other members of the particle physics community who contributed. The report readers, Dan, Myron, Andy, Richie, Stephen, Heidi, our editors, Tiffany, and Donna and Christy at the office. And we end where we started on the importance of our science and the technology that it underlies. The greater danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. We must aim high, or we will not realize the potential of our field. Discovery will be stalled, and we betray ourselves and the next generation. Onwards and upwards. Thank you very much.
Yeah, thank you, Ian, for this very enlightening talk. Very great, good summary. Are there questions? Let's look. So you can raise hands, or also you can basically put something in the chat. When I see Abai, you have a question.
Yeah.
Raise your hands. Great.
Yeah, thank you.
Go ahead.
Thank you, Ian. That was a wonderful and motivating summary. I wanted to ask, most of the detector R&D, at least in the US, has been led through funding available through high energy physics. And you alluded to the need for the EIC. Do you think that BRNs and the existing structures are sufficient to motivate something to start on the nuclear physics side generally? And if that does happen, there would be willingness to collaborate at the energy, at the DOE level between the nuclear high energy physics?
I think that the Electron-Ion Collider addresses such important physics for our field, both for high energy physics and for nuclear physics, that it makes the best sense if we pull the incredibly talented people in the nuclear physics and high energy physics communities together to address the challenges and opportunities presented by the EIC. And this must mean ultimately that the Office of Nuclear Physics and High Energy Physics need to work together to make the best possible machine and detectors that we can at this time. To not do so is a failure. Now, in other parts of the world, there is incredible excitement as well in the Electron-Ion Collider. For example, in Italy, in the UK, in many, many countries. And I know that in Europe, many people from particle physics are very excited to help to build the Electron-Ion Collider, in particular things like the silicon tracking, the maps, the LHeC GADs, the low gain avalanche detectors, the very great interest in particle ID. All these things are in common, great interest in micropattern gas detectors. And so the knowledge exists in both communities, and we should work together to realize them. And I think if we speak closely as one, perhaps we can get the DPFs, the Division of Particles and Fields of the APS and the Division of Nuclear Physics of the APS together to act as a community voice to encourage the agency offices to work together and enable the EIC to reach its full potential. Does that answer your question?
Thank you, yes.
Yeah, thank you. I see Marcus has a question. Please be short, we're a bit in overtime already.
Well, then I can also skip my question if you like.
If it's short, please go ahead.
Okay, so I really enjoyed your talk. This has been a great overview about a detector R&D, but also the importance which new instrumentation, new tools play in order to advance science, which is just here shown in your summary talk. But something where there have been also a lot of advances is the topic of microelectronics and software. You mentioned that partly when you, for instance, talked about data acquisition and you mentioned artificial intelligence, etc. What role do you see here in the interplay between the detectors and the software to not only control the detectors, but also to calibrate them and then analyze the data?
Well, software is kind of the soul of the detector in many ways. And it's the way in which we approach software in both nuclear physics and hydrogen physics is remarkably similar and can become more similar still. And I think I would like to see ultimately a global framework for all of the software approaches, for all of our slow control and our triggering and for the overall data acquisition systems in such a way that it becomes very easy for everybody to work together and for it to be relatively easy to understand each experiment systems because they're all built on common platforms. And I think that's ambitious. We're not there by a long way yet, but if we are to really utilize the talents of the high energy and nuclear physics communities, we need to make sure that there is not a lot of overhead in moving between those communities and working together on advanced software solutions. So software you cannot separate great software from great discoveries. If you don't have the software, you can't control the detector, you can't calibrate the detector, you can't make the discoveries. So it's absolutely central, as is the simulation, as is the analysis. So software is at the heart of everything we do, and we have to have the highest and reverse standards of software. Am I answering your question?
Very well, thank you very much.
Hello, Daniel. I can't hear you. I don't know. You can hear me?
Yes, I was muted. Please go ahead, but be very...
Okay. So I'll be fairly short. So thank you, Ian, for this great talk. It's really nice, and it seems like a gargantuan effort to get this done. I have a question. This basically pools and figures out a review of the entire field and makes it more efficient to get things done and achieve high goals. But I think that plays a little bit against having a very broad and large group of people working here. So is, in your view, the fact this effort makes it more efficient to get more money and offsets the sort of potential shrinking of folks working on, sorry if it's a little bit fuzzy, the question.
I mean, are you talking about the context of the IC or more generally?
In general, right? I assume that if you have sort of a distributed way of funding things, you will just have more people working and you increase the potential of overlap and people not being very efficient, but you'll have a larger pool of people working on, on the same
but I mean,
problems.
Yes, that's certainly true. I mean, there were some years ago, I remember quite a long time ago now, when Babar and Bell were both turning on. Babar seemed to have more resources and a bigger collaboration than Bell, and people expected that Babar would, for that reason, gain a particular lead, but that didn't happen.
Right.
So it's so it really is a matter of making sure that everyone can fully participate. And that means that means you need to match the number of people with the resource, but always make sure that the resource is big enough. And so that we should always all work together to maximize the funding. But then we should always work together closely to maximize the way in which people can contribute, especially in large distributed collaborations. For example, I've been a member of both CMS and Atlas now, previously CMS. And the great challenges there are there are thousands of absolutely brilliant people, but they're distributed around the globe. And it's harder for many of them to be as engaged as you would like. And this comes partly from distance, complications with communication, but also with the resources. Many colleagues lack the funding to be able to be as engaged as they would like. And so it's often more a resource limitation than a shortage of physicists. In other words, if there were more resources, you would see even more incredible physics coming out even more quickly, but it does require incredible organization to achieve that, rather than have partial engagement. So it's an optimization problem. I suspect that if you take all the particle physicists and nuclear physicists in the world at this very minute, and you listed all the different things we could actually measure at this very minute, you'll find that there are many, many great ideas that are not yet funded. Many of the great challenges I listed at the start of the talk, we are a long way from actually realizing them. Lots of experiments are required. And if we had more resources, you'll find that we would be able to do more. And so I think one aspect of all of this is the world needs to remind itself of the incredible importance of science, because science is the only way that this human species will be able to survive and thrive on this planet, whether it is climate change, whether it is renewable energy, whether it is defeating disease, whether it's discovering our universe, learning about it in all its details and knowing it for the first time, requires science. Science is truly one of the greatest things we've made, and we must continue with that. And that should be the message of the whole community.
Okay. Thank you, Ian. Deepren, I hope this question is answered.
Yes, indeed. Yep.
So, thank you, Ian,
for the
presentation, also for answering the questions so patiently. The next talk is by Carlos Munoz, and he's giving a summary about the EIC yellow report. We have learned so much about the EIC, and I think this is the summary of what we all want to know. So I will remind you again after 15 minutes that you have still 5 minutes speaking time, and afterwards we will have a discussion.
Hello, can you guys hear me?
Yes, and also your slides are up. Thank you.
Okay. So good morning, everybody. So I will be presenting today some conclusions of the Electron-Ion Collider Yellow Report Initiative on behalf of my fellow physics working group conveners, and more generally on behalf of all the participants who contributed to this work. Oops. So here's an outline of the talk. I'll be very briefly present the Electron-Ion Collider and describe some recent developments. I'll introduce the Yellow Report Initiative and then focus my presentation on the EIC detector requirements that came out of the study of many different physics processes. And I will finally conclude with a preview of what EIC reference detector may look like, and then give a short outlook on what's next. So in a nutshell, the motivation for an Electron-Ion Collider revolves around three big science questions. So the first one is to understand the distribution of C quarks and gluons and their spin inside nucleons and nuclei, both in coordinate space and in momentum space. The second one is the topic of hadronization and how hadrons emerge from the degrees of freedoms of QCD, quarks and gluons, and how quarks and gluons interact with the nuclear medium. And then finally, the EIC will investigate the environment of dense nuclear matter, trying to access and then study a regime where properties will be dominated by high resolution, high density of gluons, usually referred to as gluon saturation. So in order to access these physics goals, we need a machine that can collide electrons with protons and ions at high luminosity with a flexible center of mass energy. We also need a wide range of nuclear beams, as well as polarized protons and light ion species. And you can see here in the right plot how EIC will position itself in terms of luminosity and center of mass energy compared to other existing or future facilities. Compared to HERA, for example, the previous electron-ion collider, we're talking of an increase of 2 to 3 orders of magnitude in luminosity, with the great addition of beams being polarized in the EIC. Now, the EIC will be built at the Brookhaven National Lab in New York. Polarized protons and ion beams will be provided using the existing relativistic heavy ion collider facility, and a new electron ring will be added. There will be the possibility of having 2 interaction regions and 2 detectors, although only one is currently part of the project. So there's been a lot of activity recently, and not so recently, around the EIC project. An EIC white paper outlining the physics case dates back to 2012. And then the EIC was featured in the last US physics long-range plan as the highest priority for new construction. Later, an independent review by the US National Academy of Sciences made an assessment during the year 2017 with a report that was released in 2018 that strongly endorsed its physics case. 1 year later, in 2018, the US Department of Energy established the CD0 critical decision, which sets the official start of the EIC project. And soon after that, the site selection was announced to be, as I just said, the Brookhaven National Lab. And then the current goal is to start operation sometime in the early 2030s. The EIC community is organized around a users group and R&D activities already ongoing. There are more than 1,000 members in the EIC users group, including 255 institutions in 34 different countries. You can see here in this plot on the left that the community is very international, with about half of it coming from the US, 1/3 from Europe, and a big fraction of users also from Asia. So a major initiative taken by the EIC users group following the official start of the project was the organization of a community effort to document physics studies on detector concepts in preparation for the realization of the EIC. This initiative was referred to as Yellow Report, and because it led to the release of a massive document detailing all the studies that were done by more than 400 people over the period of 1 year. And the organization of this effort was centered around 2 different working groups, one focusing on the physics and another one on the detector technologies, with each of them, of course, having several subgroups dedicated to more specific topics. So here's a very short outline of the document divided in 3 different volumes, and I will be focusing in the physics volume during this talk, and more specifically on what are the detector requirements that came out of the study of the different physics processes that will be measured at EIC. So here's a sketch of the detector region. We follow the conventions from HERA with the proton and ion beams coming from the left and the electron beam coming from the right. So the forward region comprises the hadron end cap, and the backward region is referred to as the lepton end cap or electron cap. And these 2 end caps will be significantly different because of the different nature of the colliding beams. In addition to the central detector, a crucial region for EIC physics is the far forward region, and to some extent also the far backward region. These areas are crucial for almost all exclusive and diffractive processes, and also they were also studied in great detail during the Yellow Report exercise. So I will now go on through the different working groups and highlight some of the studies that were accomplished. Of course, I will not be able I will only be able to cover a very small fraction of them. And I will focus on the ones that led to the most stringent requirements for detectors. So if you don't see a key physics topic mentioned in the following, it does not mean that it was not considered or studied, but it's simply that it didn't drive one of the detector requirements. So let me start with the inclusive reactions working group. So this group covers a very wide range of physics, which go from global properties and Parton structure of hadrons, nuclear PDFs, twist-free PDFs, and also electroweak and BSM physics through weak neutral current measurements. Concerning the acceptance of the scattered electron, you can see in this plot that it is mainly concentrated in the electron n cap, of course. And for measurements requiring a Q-square value greater than 1 GeV squared, pseudo rapidity coverage of up to minus 3.5 is actually sufficient. Now, the main constraint originating from inclusive processes concerns PAD. And you can see in these plots, for different pseudo rapidity ranges, the large amount of negative pions compared to electrons. These need to be strongly suppressed in order to keep the statistical uncertainties reasonable. Otherwise, they dilute all the measured asymmetries. The most stringent constraints on the detector PAD capabilities come from the longitudinal double spin and the electron parity violating asymmetries, where 10 to the 4th suppression is required. Now, the next working group dealt with the semi-inclusive reactions, which covers also a wide range of physics from C-quark PDFs and C-quark helicities, 3D imaging of the nucleon and nuclei in momentum space with TMDs, and also spectroscopy. And you can see here a couple of plots illustrating the potential impact of EAC measurements on some of these observables. One of the main constraints coming from this working group was on hadron PAD. And you can see here in this busy plot, the coverage in PT and Z of single hadron measurements, assuming a 3 sigma PAD coverage as a function of eta, illustrated in the table in the left. So you can see that at high Z and at high PT, the acceptance is limited by the assumed PAD in the barrel. If it is assumed that it goes only up to 6 GeV momentum. So this effect could be somewhat mitigated in the intermediate X and Q square when combining different beam energies, and this plot shows the combination of all the beam energies actually listed here. Now, an additional stringent requirement from the CDS group is on the minimum PT of hadrons. So, and pions in particular. This is coming mostly from the lambda measurements, where you can see that the pions from the lambda decay peak at very low PT. And also to reject the lambdas that actually come from the case of sigmas, photons need to be detected down to 400 MeV. So now moving to the jets, heavy quarks working group. This is a group that covers a very large spectrum of physics again, ranging from helicity dependence of the charm production, particle propagation through matter, hadronization, quarkonia, gluon saturation, and then jets in polarized DIS, and also TMD measurements with jets. So again, I show here some projections of what EAC measurements could do with an integrated luminosity of 10 inverse femtobarn, which corresponds to at about 1 year of data at the expected luminosity of 10 to the 34. The main detector constraint coming from this working group concerns hadron PAD, and in particular, its high momentum range. You can see here in the plot, in the top plot, the momentum distribution of hadrons inside jets as a function of the pseudo rapidity for the highest beam energy configuration, 18 GeV electrons on 275 GeV protons. And you can see that PAD is required up to 50 GeV in the central region, whereas it's maybe up to 10 GeV is needed in the more forward and backward regions. The plot on the bottom shows the same thing for a smaller beam energy configuration, which is less demanding, but still illustrates the need of high momentum PAD for hadrons. The next working group studied exclusive reactions, which range from 3D imaging of nucleons, nuclei through generalized parton distributions, origin of the nucleon mass, and Wigner function measurements. One requirement of this kind of reactions is a fine granularity in the electromagnetic calorimeter. That it's needed to separate photons from pi0 decays to both remove background to DVCS, but also to study pi0 production as a way to access GPDs. You can see in the bottom plot the opening angle between the photons in the pi0 decay, and in the bottom right plot the ratio of pi0 to DVCS photons, which shows that at high X, pi0 dominates. But even at smaller values of X, their contribution are not negligible. As I mentioned before, exclusive reactions are very sensitive to the far forward detectors and also to hermeticity of the overall detector system, central plus far forward region combined. On the top plot here, it shows the acceptance of recoil helium-4, which are scattered at very low transverse momenta and typically need to be detected in the Raman pots of the far forward region. So for this process, Raman pots should be able to measure events with a PT down to 0.2 GeV. Now, for diffractive reactions, like the one we show here in the right plot, which is the case of diffracted JPSI production, the tracking resolution is also key in order to be able to see the minima of the cross section as a function of the momentum transfer T. A moderate resolution in PT will completely wash out the minima of the distribution, as you can see in the plot by the red dots. Also, exclusive channels will benefit from capabilities of muon detection. This will reduce combinatorial background in channels like vector meson production or time-like Compton scattering. Finally, photon detection in the 0-degree calorimeter is also required in order to suppress incoherent processes.
Carlos, you have 5 more minutes.
Very good, thank you. So the last working group looked at diffractive and tagging reactions. The physics topics covered here are meson structure, structure of light nuclei, and also short-range correlations in nuclei. You can see in the top plot the impact of EAC measurements, for example, on pion PDFs. And the bottom plot shows the acceptance for inclusive diffraction at EAC compared to the one at HERA, in particularly driven by the optimized far forward region of EAC. So a key measurement for diffractive processes, a key requirement for diffractive processes is hermeticity, as in the case of exclusive. We can see it here, for example, in the case of raw photo production, where the pseudo-rapidity coverage matches into acceptance in X. So any cut on the pseudo-rapidity coverage will directly cut the acceptance. Also, the plot on the right shows how neutrons from the Sullivan process that probe the pion cloud are emitted very forward in the very forward direction and can only be measured by the far forward detectors. And finally, this group also need to detect the very low energy photons down to maybe 50 MeV that come from some nuclear de-excitations and that are needed in order to separate coherent and incoherent channels. So you can see in this slide the layout of the fast-forward detectors and the detailed requirements for each of them, which are mostly driven by the acceptance and resolution needs of the meson structure measurements, actually. So this brings me to my summary that in the yellow report, we put out in the form of a table where each row corresponds to a different pseudo-rapidity region and each column to each of the detector requirements, tracking, electron PID, hadron PID, calorimetry, etc. So now I don't expect you to read from this table right now. So I will, let me summarize it in a few words. So I said the rapidity coverage from -4 to 4 units is crucial for all the exclusive and diffractive channels. The momentum resolution in the central region is driven by DIS and CDIS channels that use the hadronic state to reconstruct kinematics. A low PT detection is needed. We set 100 MeV for pions and 135 MeV for counts. The vertex resolution is driven by heavy flavor reconstruction. The electron ID is driven by DIS and in particular by parity violating asymmetries. And it's also needed for spectroscopy measurements. Very low photon detection is driven by vector meson production, as I just said, and the need to separate coherent and incoherent channels. Hadron PID is required over a large range of momentum. ECAL resolution is driven by jets in the central forward region and by DIS electron reconstruction in the backward region. And finally, a hadron calorimeter resolution of at least 50% over square root of E is needed for jet physics with a minimum threshold of 500 MeV. So in addition of all this, for the central detector, we also need the requirements I just mentioned a couple of slides ago on the far-forward region. So this basically summarizes the work of the physics working group. Now in parallel, the detector working group of the Yellow Report initiative studied the different technologies that could address these requirements and came up with a list of options for each of the subsystems that you can see in this table, which I won't go into. And they defined a so-called reference detector that will address all these constraints from physics that I outlined in my presentation. So for the moment, there were not detailed full simulations of all these different technologies. So that's the goal of the next step. That's where we are now, which is the call for collaboration proposals for detectors at EIC that was issued by the EIC partner laboratories, BNL and JLab last month, with a deadline of December 1st this year. So the community has now started this new phase in order to propose one or several concrete proposals of detector configurations that will address all the physics and all the requirements outlined in the Yellow Report. So I'll stop here and I'll be happy to take any questions. Thank you very much.
Yeah, thanks a lot for this nice talk, nice summary of the Yellow Report. Are there questions? Yeah, Sadi, please.
Okay. My question is concerning the design of the machine, mainly for machine. Several years ago, two options were considered for electron-ion collider, namely ring-ring and Linac-ring options. Question is following: is the Linac-on-ring option is excluded at all? Can you show the slide number 5?
I can show number 5. I'm not sure I'm gonna be able to answer questions on the machine, but yes, we're going for ring-ring option, but I'm not sure I can answer. Go ahead, what is the question exactly?
Is LHeC on ring option rejected at all?
I believe so. I mean, I'm not a machine expert, but I won't be able to tell you what drove that decision. But,
then you mentioned the CDRs for detector physics, but what about the machine part, accelerator part of the CDR?
So there is a CDR, so I didn't cover that part, of course, but there was a CDR that was released early this year, a little bit before the yellow report, which contains all the choices that were made for the machine.
Okay, thank you.
Are there more questions? I have one. Basically, a large amount of your physics program is related to forward or backward physics, or basically precision measurements in these regions. Do you have some estimates on non-physics backgrounds like beam halos or something like that, that maybe limits these measurements?
Now, there is a working group that is looking into that. I must say that we have some estimate, but not a lot. I mean, they haven't been included in all in the results of or the studies of the yellow report. They were not including backgrounds. I mean, the backgrounds you are referring, which are not physics backgrounds, right? But there is a working group that is looking into these kind of things, but yes, we should do it at the next phase. I would say for the detector proposal, I think we should have a better estimate of how that would impact the physics measurements.
It may become challenging, yes. Okay, are there more questions to Carlos? Okay, this seems not the case. I don't see any raised hand. So thank you, Carlos, again for this very nice talk. Next is Alex Bogacz. He will talk about the PERLE facility in energy recovery LHeC in Orsay.
Yes, good afternoon and good morning. Can I share my screen?
Yeah, please. Now you should be able to do so.
Okay. Okay, can you see my view graphs?
I don't see it.
No. Okay, I'll try again. Oh, sorry.
Looks good.
Okay.
Perfect.
Great. So
after 10 minutes, that you have 5 more minutes of speaking time.
Okay, well, I will try to stay in time. My talk is on PERLE, Energy Recovery LHeC Facility, which will be built at Orsay. This is on behalf of PERLE Collaboration. And this is the host institution, Irene Joliot-Curie Lab, a newly reorganized lab at Orsay, and then CERN, Jefferson Lab, and then institutions from UK, Dasbury, Liverpool. We have collaborators from Cornell, and finally from Butker Institute. This is the outline of my talk, so a bit of motivation first, and then I'm going to describe the baseline design of PERLE at 400 MeV full energy, talking about layout, optics, and lattices. And then I will go into separate particular systems, multipath LHeC optics for 3 passes up and 3 passes down, deceleration, which is configured with SPL style cryo module. Then I will discuss a switchyard configuration with 2-step geometry. And then finally, experimental areas, low beta inserts, 2 independent experimental areas at full energy. And finally, arc optics architecture, which is the isochronous lattice with 6-band configuration. And then I will summarize. So to motivate PERLE, that acronym stands for Powerful Energy Recovery LHeC for Experiment, and that's envisioned as the LHeC technology development facility. So that facility is actually a test bed for studying all aspects of beam dynamics for the next generation of energy recovery Linux. And that's a very unique facility with very high current, 20 milliamp current at so at 500 MeV. That actually puts us in a ballpark for beam power of 10 megawatts. And so that's a stepping stone between the present frontier, which I will show in a moment, which is 1 megawatt, and then the next on the horizon, the LHeC, which is 2 orders of magnitude higher. So again, it's a conventional accelerator transport system similar to CBAF, and it uses common beam transport for acceleration and energy recovery. And then it features very large ratio of full to final energy, which is 70:1. And again, it's a very efficient multi-pass recirculating LINAC with 3 passes. So, and again, it originated as a test facility, but now it's also envisioned as the user's facility. Will provide venue for studying elastic electron-proton and electron-ion scattering, as well as collision of photonics, which is collision of electron beams with lasers to produce Compton backscattering in different frequencies. So the landscape for ERLs, it's here it's a very convenient way. If we plot average current on a log scale versus energy also on the log scale, then we'll see the diagonal dashed lines, they refer to different beam power. So when I was referring to and then we throw all the existing and planned and previous called legacy facilities on this graph. So we see that this energy or power frontier, which we're talking about, was established a few years ago by our free electron laser at Jefferson Lab, which was a relatively low energy, 150 MeV, but very high current, 50 milliamps. So that's this 1 megawatt energy frontier. And that we also are planning to do low current, 100 microamps at 5 passes at the top energy of about 7.5. This is a planned experiment also along that line. So we see far away, there's the LHeC, which is the ultimate goal for using that technology. And it's like 2.5 orders of magnitude above the frontier. So obviously one would need to have a stepping stone, and PERLE is actually falling near this line of 10 megawatt. So this is basically why it's so interesting. Here we have PERLE, the layout, base layout. So it's a relatively compact accelerator, 30 by 6 meters, and it's a vertical stack about 1 meter. So here we see that this is on one side we have 3 vertical stack of 3 arcs, and on the other side we have another 3 arcs, and each LINAC is basically configured with a cryo module for cavities providing about 82 MeV energy boost. And again, this is the top view and the side view, so that different arcs in the stack are separated by 45 centimeters. And here we have the parameter list, so injection at 7 MeV, and then again, a very high current bunch per charge of a nanocoulomb here, and some other parameters. And it's meant to operate in CW mode. So how would it work? Well, we start from the source, we go through the merger and inject the beam for acceleration at 7 MeV, and then the beam actually goes 3 passes through this set of arcs and common LINACs. Here we see the side view. The last arc, which is here at 500 MeV, is actually providing additional path length difference. So all the arcs 1 to 5, lower energy arcs, they basically, the path length is a multiple of RF wavelength, with exception of the last one. So in this last pass at 500 MeV, the there is additional path length of half of the wavelength, which puts the beam here at top energy at the beginning of the LHeC in a decelerating phase. So that's why I mark it in blue. And now the beam is actually going and is being decelerated in 3 passes. So you see at the end, the beam is extracted at 7 MeV. So this is in a nutshell how this 3-pass up, 3-pass down arrangement works with this. Here, the blue elements, they are bands, red are quadrupoles, and those have cavities. So to look at the synchrotron radiation effect with the geometric radius, just to be sure, this is a very compact machine, but nevertheless, the total energy loss for this 3 passes up, 3 passes down is in a KV region, and other effects on beam quality are completely negligible. So we can forget about synchrotron radiation effects. So going to the next, so the LHeC is actually configured with SPL style cryo-module. Those are developed at CERN. So this houses 4 5-cell cavities, and this is altogether about 7.5 meter long. So this is actually put here. And the LHeC itself has this reinjection chicane where the beam is being injected from the merger, and also 2 other magnets for higher passes to close the bump. And then there's a weak quad doublet. So in principle, this is the whole thing is about 10 meter long, which constitutes about 27 RF wavelengths. And again, we are using frequency superconducting RF, 802 megahertz, 5-cell cavity. So that's the RF wavelength, 37.4 centimeters. So this 5-cell cavity is about 93 centimeter long. And it provides, it's set for a gradient, pretty ambitious, 22 megavolt per meter. We're getting to that point. And then so each cryo module will basically give you the boost of about 82 MeV. So the optics for that, the horizontal and vertical beta, ideally it will be a parabola because it's a drift. But for the first pass, this parabola is actually a little bit distorted, and it prefers if this quad doublet is set to 0, it would prefer the same values of betas and alphas in both planes, but this is not a favorable thing to be injected from the merger. So that's why there's a weak quad doublet, which is actually at 7 MeV, which allows you to start with different twist functions, very much different depending on the setting of this weak doublet, and it provides almost identical values at the end for the first pass. So if we put all the passes, so again, in each LHeC we have 3 accelerating passes and 3 decelerating passes marked in red and in blue. And because we share the same arcs for both acceleration and energy recovery, therefore there are some constraints here. So basically those are accelerating and decelerating LHeC connected. And you can see that this effect of very weak doublet at 7 MeV is actually translating to slightly different beta functions, which is a very, very favorable optics. And here, those points where I have A1, A2, this is where the mirror symmetric arcs would go. There at the moment shrunk to the point. So at the end of each LHeC, we need to separate different energy beams, and this is done in a switchyard. So here I have the higher energy end. So we have one, at the end of the LHeC, we have one beacon magnet, which actually separates. So this is the lowest energy, the medium energy beam, and then the highest energy beam. And this is configured in a form of a 2-step staircase, and it actually, so that it has to be an achromat. So those quadruples at the middle here in this flat piece, they basically suppress dispersion. So this would be the corresponding optics with beta functions, red and green, and dispersion, vertical dispersion, which is this black curve. So we see here different energy path for different arcs, and we see that actually the dispersion is suppressed by the 3 quads, except the last path where we actually built a chicane, which dispersion is closed by geometry. And this last arc, which is at 500 MeV, actually hosts experimental area, which is I will describe it next. And again, it's a separation of 45 centimeters, and it's configured with a normal conducting magnet, which has been designed at CERN, about 33 centimeter, about one Tesla, providing this this switcher. The similar arrangement is done on the other side, where the energy ratio is 1 to 3 to 5, which looks like has slightly different geometry. So that experimental area.
4 minutes left to speak.
Okay, well, I will speed up. So the experimental area is done at the top energy, and it's actually like a mini low beta squeeze. So we see that it goes from 10 meters to 10 centimeters, that between 10 and 30 is fully tunable. So there's a triplet, and then that's where the experiment would be placed. And then there's a pair of doublets to close it. So presently, we have in this design, baseline design, the length of this free space for experiment is 2.7 meters, but can be increased in increments of 131 centimeters. You'll see next, but it can be expanded to, let's say, 4 meters, 5 meters, and so on and so forth. So going to the arc, this is 180 degree arc. It is actually configured with 6 magnets. This is flexible momentum compaction. So you see that dispersion is actually an achromat, but the important thing is momentum compaction, which is this integral of dispersion overall, which is important because it gives you a time of flight for a particle with of momentum. And ideally for isochronous, we should be able to control it. So see, here's something that is close to 0, which means that areas above and below basically kind of bounce, and we have but we have flexibility of adjusting this. So to put things together, spreaders, arcs, and recombiners, it's done arc by arc. So on one side we have arc with those energies with ratio 1 to 3 to 5. And then you can see that there's large negative contribution to momentum compaction coming from the spreaders and recombiners. So to balance that, there's a positive tune-up for arc1, and then gradually that is a negative contribution from spreaders and recombiners becomes smaller and smaller. So at the end, we basically have that tune for the highest arc. And here you see that the arcs are actually, there has to be integer of RF wavelength, and they, for reason you will see above, it's actually 56 RF wavelength. And here there's the other part with arc 2, 4, and 6, and they have slightly different 57 RF wavelength. And the last arc, which actually provides this additional half wavelength, is 60.5 of RF wavelength. And why is it so? Well, since this is supposed to have the same time structure like the LHeC, so there's a time structure of every bunch is injected with 25 nanosecond injections. So for this RF wavelength, that means that the spacing between consecutive injections is 20 RF wavelength. So one would like to actually paint a uniform pattern of accelerated and decelerated bunches across the machine. So here, if I look at the LHeC is 27 RF wavelengths long, and its injection starts at bunch number 3. So, and I put a path length for different passes in units of RF wavelength here. So what we have here, every 20 bunches, there's a fresh beam injected. So if after the first pass, we have this situation in the LHeC. and it makes one pass. And if it were a multiple of 20, meaning that N1, the remnant, would be 0, basically then the next injection would basically collide with this bunch here. And this is not a good situation. So what we choose, we just deliberately put it into the design of the arc. So if we put 7, you'll see that this will be number 10, which is good. And then the next one, next turnaround, pass 2, we have a choice of N2. We choose 6, so we have 16. So you see what happened here, that this 20 is divided into almost 3 equal. It's 7, 6, and 7. So now there's the last pass, which is pass 3, accelerating pass, and we have a choice of 3, 10, and 17. So we choose 10. So you see what's happening. We get 26, and also since modulo 20, so it's 6.5. So those are actually decelerating already bunches. And then you get the picture. So we put 6 for the next decelerating pass, so we get 12.5. And then to complete the picture, 7. So we end up with this situation. And it's a very favorable for high current machine, because we have 3 accelerating passes and 3 decelerating passes simultaneously in the machine. So we want to avoid a collective instability. So we don't want those bunches to be close. They are basically ideally equally spaced for perfect acceleration. And this is actually why that pattern translates of actually arc path length, which again, for one stack was 56, and for other one was 57, and then 60. So to conclude, what I have described is a baseline design for PERLE at 500 MeV. So it describes a multi-pass LINAC for 3 passes up, 3 passes down, and then switch out configuration with 2 beacon magnets. And then it's equipped with a pair of experimental areas at 500 MeV. There are these low beta inserts. And finally, there's isochronous arc, 6-band arc architecture based on flexible momentum compaction. And as for next steps, this actually was the second edition of that baseline design for PERLE. We have a full plate of things to do. So those are next steps for 21, 22. So a complete injector design, using previous EIC booster from JLab design, then complete end-to-end tracking validation of the design that I have just shown you. And then moving forward, those spreader, when we combine a beacon magnets, we need to set the specs and do some prototyping. And then on the RF, we need to look at higher order modes, design and test of addressed cavity. So that's experimental work at Jefferson Lab that is actually moving forward this 802 cavity design. And then preparation of Alice gun for installation at Orsay. And then finally, we are developing by the end of next year, technical design report with the goal of first beam in the mid-20s. And finally, we want to integrate PERLE into the European roadmap for accelerator. That's activity that started a few months ago. And then the important message right now is basically telling us that both FCC-eh and recent International Linear Collide are proposed as energy recovery colliders. So they use some components of energy recovery. That means that there's a significant increase in luminosity and substantially reduced power consumption. So that puts PERLE as a centerpiece for future high energy physics, particle physics, and nuclear physics facilities. Thank you very much. I had some special thanks to my colleagues who inspired this work. Thank you. Hello?
Thank you, Alex, but I don't know where Daniel is. You lost the chair. Maybe there's a co-chair.
Okay, now you hear me. Thank you, Alex, for
You're
the
welcome.
very nice talk. Are there questions? I think we have to rush a bit because we are quite over time.
Okay, well, thank you. I will stop sharing.
Yeah, so I encourage everybody to join also the Gather Town meetings and maybe have an informal discussion in the virtual conference room. So the next talk is by Miguel, who already set up his slide. Good morning, Miguel. Miguel will report about jet-based measurements of Sivers and Collins asymmetries at the EIC. It's a physics-related talk, while we had so much technical talks until now. So Miguel, I also will remind you after 10 minutes that you have 5 more minutes of speaking time.
Okay. Okay, so hello everyone. Yeah, today I will give a brief presentation on the prospect of jet-based measurements of some of the key flagship measurements of the EIC, which are Sivers and Collins asymmetry measurements. So the EIC will be a jet factory. It's a collider after all. And what it will make it unique and distinct is that it will produce jets in nuclear DIS and in proton polarized DIS, neither of which has been done before. And you know, there are many processes that produce jets and that allows us to study different physics. And I flashed here some event displays that are trying to illustrate that. I will not try to explain you what is the full breadth of jet physics potential at the EIC. I will concentrate in one example. So in the case where you have a transverse polarized spin in the proton target, in the proton beam, and you can study spin orbit correlations. And I will explain that in a second. But that leads to azimuthal asymmetries. And in fixed target experiments, this is typically done by measuring one particle, one hadron at a time, and correlating that with the hadron, with the target spin orientation. So you can study asymmetries in that way. And one of the key aspects of these asymmetries is that they reflect a correlation between the proton spin and the quark momentum. So that can be encoded in the so-called Sivers function, which you can see in here. An example is dipole deformation in either D or U quarks. And this is a figure from the white paper. This is what we would like to measure, as was explained also in the previous slide by Carlos. And the fact is, though, that one cannot really measure that Sivers function, which is a TMD, transverse momentum dependent PDF. But if you measure only one particle at a time, you get a blurred image. And what I mean by that is that you get a convolution of a TMD PDF and a TMD fragmentation function that acts like a convolution kernel. So if the measured cross section, you would like to deconvolve that blurring and get the TMD crisp image. And that is not easy to do. And if you try to constrain this by just measuring the CDIS cross section, both because you have both two unknowns, the TMD PDF and the TMD fragmentation function, any parameters that you extract, they would get like huge correlations. And that's exactly what we observe if you were to use CDIS data alone. And that can be in part compensated if you try to use other data sets, but then the global analysis gets very quickly complicated because the issues of TMD factorization and universality are not completely fixed. Fortunately, the collider era will bring us another tool, which is jets. Which here I'm showing you the diagram that shows jet production at the leading order on the left-hand side and how that might look like in simulated detector on the right-hand side, so an event display. So in theory and experiment, this measurement or this theory is actually rather clean, and the measurements are also very clean. And they would allow us to really do new type of measurements and addressing the key science of the EIC, but with different and new tools. So this idea is relatively recent. You can trace it back to these two papers that by Liu et al. And Gutierrez et al. In these two PRLs. They propose to use jets to study quark TMDs and their evolution. And I quote from the authors of those papers that the main point is that you get no fragmentation functions. And therefore that's an advantage because that allows you to really measure the TMD PDF. And you can intuitively get why this is the case because you want to measure asymmetries at the parton level. And neither of the hadrons that are produced really correlate very strongly with the parton. But if you collect the ensemble, you collect them all, then the jet axis actually is a very good proxy for the parton axis. So that's the reason why they are actually very useful. So we have simulated what is the jet performance that we expect at the EIC. At the EIC, we will most likely use the energy flow algorithm, and what we are using so far in fast simulations using the Delphi's implementation of that algorithm. And where we are using to get the parameters, the reference that we used to get the parameters of such detector are in the recently released yellow report. So this is just performance plot that you can expect at the EIC. So just as a figure of merit, at 40 GeV, we expect to have like a 10% energy resolution. And with that type of resolution, and with those type of studies, and using the rates that are expected at the EIC, we projected some of the key measurements, and in particular, the lepton jet Sivers asymmetry. In this measurement, what you do is to measure the electron and then the recoiling jet, and you measure the azimuthal angle and how the transverse spin polarization of the proton really leads to modulations. And the observable here shown on the y-axis is the sign moment of that modulation when you have transverse polarized proton. That asymmetry is actually only a few percent, but it has a large error. We do not have a very precise knowledge of the Sivers functions at this moment, even at large X. What I'm showing you here in the error bars is the projected statistical uncertainties, and the bin widths are reflective of the smearing that you can expect in this variable, which is the imbalance between the electron and the jet. So this is our projection, which you can find in this paper, and this is based on the formalism developed by Liu et al. That you can see also in this paper here. So this is for jets that are around 15 GeV or so. Keep that number in mind. Of course, one would like to do this type of measurements in a very highly multi-differential way, which requires large statistics, large integrated luminosity. So the question that you might ask is, well, those were fast simulations, and can we really measure the momentum imbalance well enough to really probe the TMD region? And the answer is yes. And this is a spoiler alert, because I'm going to talk about this in much more detail in my talk on Thursday, when I will present preliminary results on our H1 analysis. So what I'm showing you here is the QT spectrum. And compared with a TMD calculation and a fixed order calculation. And you can see that the TMD calculation describes the data over a wide range. And typical threshold for the TMD framework that people apply is about QT divided by Q of about 0.3. So like right at the middle of this plot, we can definitely do some differential measurements along this variable and probe TMDs in this way. We are going to do this at H1 with unpolarized beams, and then looking forward for the EIC for the polarized case. Now, that is just one type of measurements. Now that we can identify the back-to-back topology, and we can constrain really the back-to-back topology to be in the TMD dominated region or TMD sensitive region, you can now look at the jet substructure, and jets really have a rich substructure which encodes rich dynamics, including TMD dynamics. So you can study substructure or more, which include, of course, the fragmentation, to study TMD fragmentations and also all sort of evolution effects. So you vary scales, not just by varying the Q-squared of the event, but also by varying the scale of the jet itself. And you can also study TMD evolution in that way. So one example of what flagship measurements that you can do with jets fragmentation is a transversity measurement. So transversity is a distribution of transversely polarized quarks inside transversely polarized nucleons. So this was proposed in 2008 by Feng Yuan. And then the theory has been developed over many papers, and this has actually been measured by the STAR collaboration at LHeC. You can see here a prediction by Kang et al. And the experimental data. So this is an asymmetry that you measure when that is induced by this transversity that shows up in the azimuthal modulation of hadrons with respect to the jet axis. So you define the angles with respect to the jet axis. So the data here is compared to the theoretical expectation. Data at this point has had large errors. These measurements are getting better and better. With new STAR, more recent STAR data with larger luminosity. So what we can do at the EAC is to really complement, yes, we can really complement those studies. So you can now also measure the azimuthal angle of hadrons inside jets, but at the EAC, and DIS in general, you have an electron axis. So now instead of having just one axis, you have two axes, and that actually means that the type of studies that you can do is actually more, they are more complex. You have more variables to play with, and you have more control over the kinematic variables. So the main idea here is that you would like to measure the longitudinal fragmentation of jets and the transverse fragmentation of jets. I showed you here two examples of theory predictions compared with Monte Carlo generators for some EAC kinematics. The theory is given in this paper, and you can see it in here. Basically, you can probe TMD fragmentation and separate the transverse momentum that is coming from the initial state with the transverse momentum that is coming from the final state. So that's the main point of this. And this type of measurements can also be performed at HERA, and we're going to do those measurements before the EAC. But at the EAC, of course, the main point is that you would like to measure this with polarized beams, and you get modulations, asymmetries, which in this case are called the Collins asymmetries. And these are our predictions and projections for this hadron in jet Collins asymmetry. The error bar actually is barely visible. These are three different intervals of X, and for blue is the pi plus, and orange is pi minus. And the bin width is reflective of the smearing that we expect in this variable. So one of the things that are coming across all these hadron in jet measurements and substructure measurements in general for DIS, and especially at the EAC, is that those measurements will be very highly differential. There are many angles that one can play with. When you have two axes and you have the hadron with respect to those axes, and you can also control the angle between the electron and the jet and so on. It gets very complicated very quickly. And it is actually more, the requirements of the dimensionality are more than in traditional cities where you only have one axis. So one of the questions that naturally arises is how you can really control unfolding in 8 dimensions or more. I mean, 8 is like the lower limit of what you need to do this type of measurements. You might end up with 12 dimensions or something like that. And that is tricky to do with traditional methods. Fortunately, there has been recent advances on machine learning for unfolding that really help us to address this issue. And if you want to know more details, you can tune to my talk on Thursday, I will give you some demo of a first use of such techniques. And the EIC will really give us potential for an unprecedented jet program, jet physics program. And the reason for this is that we will combine superb tracking, superb PID, and full calorimetry with high luminosity and beam polarization. So the type of jet substructure measurements that we will be able to do with this instrument is just unlike any previous collider in history. And I think that's where the field is likely to move. So jet substructure will give us a key for novel TMD studies. You already can see in the literature examples on this, on how, for example, to use grooming techniques to enhance sensitivity to TMD PDFs or fragmentation functions. Or also there is literature on how to use jet axis. So the difference between the standard jet axis and the groom jet axis or the WTA jet axis, that angle is literally a transverse momentum dependent variable, and you can probe PDFs and the evolution by looking at these three angles and looking at all sorts of correlations. There's a recent example just last week. There was a paper by Liu et al. On how you can actually use a WTA axis, a winner-take-all axis, to study the T-odd nature of jets. So you can study T-odd functions, which were thought to be impossible with jets. And this is really a new tool to study particle spin and hadronization at the EIC. And more recently, I think not yet specific for the EIC is the possible application of declustering. And why I say this is because there has been a renewed interest in spin effects in jet fragmentation. So this is an old subject, but there has been recent renewed theory thrust with proposed new observables and new calculations, more precise calculations. So you can see the spinning gluons papers by Ian Moult and company that use energy correlators. And there's a recent paper of this year, a follow-up paper or a different independent paper that uses the Lund plane declustering for the jet, shown here, appeared in the archive a couple of weeks ago. And those are related and try to study spin effects and quantum interference that arise in the shower when you have when you take into account the spin effects. And I really think that this would allow us to address key EIC science goals. It's just a matter of time before we get EIC specific developments. And what I think is cool about this is that it really allows us to explore smoothly the transition from a perturbative regime to non-perturbative regime by just varying some parameters that are in these observables, like the angle between the prongs in the clustering scheme, for example. And you could really control from a controlled PQCD or perturbative regime, you can extrapolate to the non-perturbative regime and explore the same physics we can explore with other observables, like the Collins fragmentation, for example. So that brings me to my summary. So jets can really help us to address key science goals. And I didn't touch on all the things that jets can do for us at the EIC. I just focused on TMD studies. And jet will be a new tool for those types of studies, but also they will open up a completely new class of studies by giving us jet substructure techniques. So there is no analogous to that in cities. And the EIC jet studies at the EIC will exploit an unprecedented combination of tracking, PID, full calorimetry, and beam polarization. And I also should mention high luminosity. So the theory demands very highly dimensional measurements with all sorts of angles and all sorts of variables. And because we're measuring jets, we need to do unfolding. And the unfolding is a challenge if you want to do it in multiple dimensions. And that is actually a great challenge that can be addressed with machine learning techniques. And I just want to finish by saying that given recent theory developments, the HEDA data really provides a great opportunity for us to build and create a EIC Pathfinder program. So thank you.
Yeah, thank you, Miguel. Very nice talk. Are there questions? We have a bit time for discussions. I have maybe two, but please be short. On the right, you show the detector layout. Do you prefer to have the solenoid inside or outside of the HCAL from a jet perspective or from the substructure perspective? Yes,
I think that's a good question, and that question has come up recently quite a few times. I think we really need to do the detailed simulations, giant simulations to answer that. I suspect that the answer will be that would be beneficial for jets, but not only for jets, because as you know very well, what we really need at the EAC is to be able to reconstruct the Q squared and X of the event by measuring all the hadrons in the event. And so the performance to do that is very similar to the jet performance. And if we can get the energy flow implementation as best as possible, that will help not only the jet measurements, but also the inclusive measurements, which of course is a central piece of the EAC program. So my short answer is that I don't know, and we need to answer that question quickly. Okay, I have more questions to you in mind, but this maybe we can have in GatherTown then. Is there one other urgent question to Miguel? This seems not to be the case. So the next speaker then, thank you, Miguel. Thanks a lot. Thank you very much. Next speaker is then Alexander Korzenev, and he will report about the SPD experiment. You're already up. Can you share your slides, please?
1 second.
Perfect. Looks good.
Can you hear me?
Yes. I will also remind you after 10 minutes that you have 5 more minutes of speaking time.
Okay, good. So good morning or good evening, depends on which continent you are. So I'm going to speak about the SPD experiment, which will take place at the accelerator complex NICA in Joint Institute for Nuclear Research in Dubna. So the SPD stands for the spin physics detector. It is a universal facility with the primary goal to study unpolarized and polarized gluon content of proton and neutron. So we have about 300 participants in our experiment from 23 institutes from 10 countries plus individual contributors. So let me say a little bit about the history of the experiment. So SPD project was approved by the Program Advisory Committee about 2 years ago in June. And this winter we released a conceptual design report, CDR. And basically this year will be dedicated to the discussion and interaction with Detector Advising Committee. And we plan basically to prepare a technical design report within this and next year, within 2 years. And basically, the beginning of data taking for SPD is foreseen after 2025. So it's clear that Detector is big and it will not be built in one go. So that's why the physics program is basically subdivided in 2 parts. So the one is the main part, basically the study of gluon content of the proton and neutron. So that requires a full the maximum energy of accelerator and the full luminosity, and the NICA complex is presently not yet operational, but it will be start operating in the next year. So that's why it's basically will be the second stage. But the first stage will be with lower energy, probably lower luminosity, but it's still exciting physics like study of elastic scattering, hyperon production, study multi-quark correlation, exclusive reaction, open charm, and so on. And now let me say a few words about the main physics program. So we're going to probe the gluons in proton and neutron using these 3 main reactions. The first one is Chermonia production. So at energy of SPD, this vertical line, so it's about 200 nanobarn. This open charm production, so it's around 10 microbarn, and the prompt photon production, so it is the lowest cross section is around 30 nanobarn. So I again refer to our physics program, to our physics paper, where we describe the physics which we're going to study. So that will be the test of TMD factorization, study of linear polarized gluons in unpolarized nucleon, hadron structure and heavy harmonia production, non-nucleonic degrees of freedom in deuteron, gluon polarization with longitudinally polarized beam. So this study of these three effects and study of transversity in tensor polarization of gluons with a deuteron. Now let me compare SPD to other spin experiments. So first of all, SPD is collider experiment, and we have a proton, well, we have several options for the beams. So they can have both proton-proton polarized and also deuteron-deuteron, and also in fact, its option, which is possible, is to have a proton-deuteron beam. So because we have a two injector and one could provide a proton and another deuteron, but only one of them is polarized. So in case of the proton-proton mode, the maximum energy which we can achieve in the center of mass, so it's 27 GeV, and the maximum luminosity is 10 in the power 32. This for proton-proton, so this for deuteron-deuteron, so the center of mass energy is factor of 2 lower, about order of magnitude lower for the luminosity. Now let me show this kinematic domain which is occupied by SPD. So this is this shadow area. So you can see, so this is intermediate and high values of X. So it's basically domain which is normally covered by the fixed target experiments. And indeed, when you look our neighbors, so this energy scale, so square root of S, so you will see, so this experiments which were before NICA, or this neighbors from the left, this fixed target experiment, and of course, our neighbors from the right side, so this is RHeC. But advantage of SPD, so this is not a fixed target, but collider experiment. So, and basically, we have a nearly 4 pi coverage, it's more uniform acceptance. Now, let me shortly describe our accelerator complex. So these polarized protons and neutrons, they ejected at this point. So this is light ion injector, LU20. So they injected to the nucleotron ring. So there are two accelerators in this building, but we use only one of them. So this is nucleotron. And then once it's accelerated up to, let's say, 13 GeV, so this is the maximum energy or momentum which we can get with this nucleotron. So there are two options. So either beam is transferred to the test beam area or to the collider. At the collider, we have two experiments. One is MPD, another the SPD. Detector set, which we have in the SPD, in principle, is similar to, let's say, generic collider experiment. So in the center, we have a vertex detector or inner tracker. This is silicon detector, which is a pixel or strip detectors, which is surrounded by this. So it's basically mainly used for reconstruction of D-meson vertices. Around this vertex detector, we have a straw tubes, and around straw tubes, we have a PID system, which should be the time of flight system, or we also discuss this aerogel option. This is Cherenkov threshold counter. So altogether, this is in the solenoidal magnetic field, which is produced by these 6 isolated coils. Again, if you go from inside to outside, so the next detector would be electromagnetic colorimeter. And finally, we have the muon system. Okay, so basically, since this detector, this experimental hole is located on the sandy ground, so that basically the weight of the detector is limited by that. So we cannot, weight cannot be larger than 1,200 tons. And basically that limits the size of the detector. So it's, you see the diameter, it's around 6.5 meter. Now let me go detector by detector. system. So our superconductive, our magnetic field is produced by 6 isolated superconductive coils. Yeah, so you can see the 6 of them. And the maximum, the total current which goes through one coil is around 600 kiloamp times turns. And it means that magnetic field inside this longitudinal magnetic field is around 1 Tesla. But of course, if you go closer to the coil, so it goes up to say, 3 Tesla. And the cable, so we plan to use the same cable as those which are used for the nucleotron magnets. So they are hollow superconductor with a 2-phase helium flow inside, basically. So the temperature is 2.5 Kelvin. So the tracking system consists of inner tracker. Let's say it's our main tracker. So inner tracker is which we call a vertex detector, has 5 layers. So 3 inner layers, we plan to have it built of monolithic active pixel sensors, so MAPs. And for the 2 outer layers of the vertex detector, we plan to have a strip detector, so the double-side silicon strip detector. Basically, so the vertex resolution which we can achieve, so it depends on configuration, but it can be from 50 to 100 micrometers. And the fact why we want to use these maps, using those maps instead of strip detector, so this signal to background ratio for dim meson peaks basically improved by about factor 3. Then straw tracker, we plan to use 1 centimeter diameter straw tubes, which can provide us the special resolution around 150 micrometers. And so let's say for the barrel part, it can be 30 double layers, let's say with a Z orientation and 2 ±5 degree incline layers. In addition to the space, we plan to measure the charge, which can actually help quite a lot for PID, particle identification, for the very soft tracks, which cannot reach, let's say, time of flight, but let's say start tuning inside. So this energy deposition can be used for particle identification.
Alexander, you have 4 more minutes.
Oh, okay. So the particle identification can be done, in our case, so it should be time of flight system, which we consider 2 options. MRPC option, which is used in 2 other experiments in NICA. And presently, we also consider the option with the scintillator tiles. In both cases, the resolution is 60 picosecond. Or we also, inside of this TOF system, it will be, we plan presently, we think to have also aerogel. This is a threshold Cherenkov counter. So, and then if we look, let's say, what I already said, so for very short tracks, so we can use those which cannot reach the time of flight system. So we can use energy deposition in the straw detector, let's say, to separate pion and kaon up to 0.7. So if tracks is relatively long, like 1 meter, so it can reach TOF. So it's up to 1.5 GeV TOF will be used. And for high energy, let's say up to 2.5, so we can use aerogel. This our spectrometer is also equipped with a colorimetry and range system. So the colorimeters, it's sandwich detector with the number of radiation lengths 18.6 and range system, which will be used for muon identification and rough hadron colorimetry. It has around approximately 4 nuclear interaction lengths. The design follows closely the design of Panda. It's the same group which is built in for both experiments. We also have a polarimetry and luminosity control with a beam counter, which also has 2 parts. One will be located inside of the beam pipe and another with a scintillator tile around. And the second detector is 0-degree colorimeter, which is 14 meters away from the interaction point, let's say in this place between two bending magnets, where these two beam pipe are merged to a single one. Okay, it's also a scintillator detector with layers of absorber. Just before I conclude, so I would like to show a few slides with our Monte Carlo study for these three main reactions for the gluon PDF. So this first one is Chermonia production. So this estimate is done assuming 10 to 7 seconds of data taking. This is approximately 1/3 of astronomical year. During this time, we can produce 12 million J-psi, which decay into muons, and after all selection, so what you can see in this figure, it's around 4 million J-psi. So we can use a transverse single spin asymmetry, which probes the Sivers functions. And what you can see on these two bottom plots, this is prediction, which is done in generalized pattern model. So this is a reference and assuming different distribution function for Sivers and different hadronization models. So you can see this our error bars. So depending which model used for the prediction. So let's say in this case is our error bars uncertainty invisible. In this case, you see it's still let's say it's you're close to 0. So this asymmetry which is predicted is quite distinct from 0, and we can really contribute to its measurement. Sorry. Then the second reaction is a prompt photon production. So it's a very clean probe to study Sivers distribution function and V3 correlation. So it's proceed without fragmentation. So it's free from Collins effect. But in addition, just before I start speaking about the asymmetry, I also would like to say that it's quite big. So in the region of intermediate and high X, there is quite big disagreement between data in theory for the cross-section measurement. So basically this is fixed target experiment, and I just remind again that SPD is a collider, and so it's slightly different measurement type of measurement. So but we occupy exactly the same region, so we probably can resolve this issue of disagreement of theory and data. And again for the asymmetry, so this is a yellow curve. Yellow line. This is the prediction, and this is our uncertainty. I'm almost finished. Yeah. For the D-meson production, yeah. Again, the golden channel is decay to pi and Km, and again, so this prediction from the theory, yeah, for the single spin asymmetry and our uncertainty. Again, so we can contribute quite a lot. So then I come to my conclusion. So the NICA collider will start operation in Joint Institute for Nuclear Research in Dubna at the end of next year. So the center of mass energy is 27 GeV in proton-proton mode. So we can measure, do the measurement with a proton-proton, proton-deuteron or deuteron-deuteron beams. Also foresee different polarization, longitudinal transfers for the beam. And the SPD is a universal facility with a primary goal to study unpolarized and polarized gluon content. And our collaboration this winter released a conceptual design report. And his proposed program, which covers at least 5 years of data taking. And we plan to prepare this technical design report within 2 years. And the first data of SPD, so it's after 2025. Thank you.
Yeah, thanks a lot for this very interesting talk. Are there questions? A few minutes for discussions. Please raise your hands or just talk if you have something. I have one question about your bunch crossing rate and basically about the readout rate and your trigger strategy. What are basically your benchmark parameters that you have?
Yeah, so let me see whether I have one slide. Yeah, the bunch cross every 76 nanoseconds. Yeah, so the crossing rate is 12.5 megahertz. All right, and basically, if you basically we do not plan to have a hardware trigger, but it will be online filter. Basically, with this rate, we can have about 20 gigabytes per second or 200 petabytes per year, right? So, and this is really a lot, even if we have a computer farm here in Dubna, so it's too much. So it's online filter, which we plan to use, will reduce this rate by order of magnitude. And with this 10 petabytes per year, so it's fine, so we can manage.
Because you mentioned that basically data or the accelerator starts running next year, but the experiment start only...
yes, it will be at the end. So you see at the moment, yeah, I can show the aerial view. So basically the nucleotron is running since several decades, but this collider is built from scratch. So this photo from beginning of this year. And you see it's not completed. So it means that basically according to current plans, so this accelerator start running, we'll have a first beam in collider at the end of next year, 2022.
Okay. Yeah, thank you. Are there more questions to Alexander? This seems not to be the case. Okay, thank you very much.
Thanks.
And good luck for the next steps of your experiments. The next talk is by Oliver Fischer. Hi, Oliver.
Hi.
And you talk about BSM physics at the LHeC and also about the FCC-eh.
Yes.
I also remind you after 10 minutes that you have 5 more minutes of speaking time, and then we will have a short discussion afterwards. Thank you.
Sure. Thank you very much for the introduction. And thanks to all previous speakers and everybody who's still here. I will give you an overview of a BSM physics at the Large Hadron Electron Collider and also a little bit over the FCC-eh. The emphasis in recent years was the LHeC. So first of all, I want to give you the good news. If you haven't heard already, we have managed to put out an update on the project last year on the archive, which has been accepted for publication, and you can find it here. And I will not go into any details. I invite you to read it. Many interesting and connections to other existing projects and all updated details can be found in there. So one thing that's kind of new is that we now consider an electron beam energy about 50 GeV for cost saving purposes. But many of the things that I will discuss in the following still consider 60 GeV, and I'm not sure if we will change that also soon. The difference is not very large in terms of results, for BSM at least. And the earliest start that we foresee for the LHeC is 2032 at run 5 of the LHC. Here is an overview in this overview, updated paper in chapter 8. We have a long list of studies that have been carried out for the LHeC and in parts also the FCC-eh on BSM physics. So I will not go through all of this in detail. I mean, this is what the paper is there for, with a lot of references included. Let's first have a look at the motivation, or remind ourselves why we discuss beyond the standard model physics at electron-proton colliders or in electron-proton collisions. So the first point is important. The motivation for beyond the standard model is as strong as ever, maybe even stronger than before now with the recently enforced G-2 of the Munoz anomaly and then the flavor anomalies at LHC, but there are others. I invite you to have a look at this website here, which lists all the known and corroborated anomalies in high energy physics. You can also contribute and help updating it and grooming it for posterity. Some points that have been raised in the past: electron-proton colliders are really ideal laboratories to study common features of electrons and quarks. This means in particular physics that is produced electroweakly or in vector boson fusion, but also leptoquarks, or beyond the standard model physics that has a lot of very jetty final states and forward objects, all of which is difficult to study and find at the LHC for reasons of backgrounds and whatnot. One of the upsides is that we have very small backgrounds because there is no QCD in the interaction between the initial state particles. And also there's essentially absence of pileup. So this means that it's very clean environment, and the detector can really study in great detail and has very limited restrictions in terms of triggering and whatnot. There's a downside in NEP collisions now compared to PP collisions. The production rates are comparatively small, And that's mostly because of the restrictions of the center of mass energy. So having a larger electron beam energy would help. Also with respect to phase space, I mean, I must say, compared to electron-positron colliders, the interaction, the sort of mass energy is actually quite high. So this is, it's not as small as it might appear here. And then recently there has been a strong engagement from the theory community, and which is summarized in chapter 8. You can see there are almost 100 references. I invite you to have a look. They are best structured reasonably, and we can stay in touch and discuss about future ideas. In what follows in a few remaining minutes, I will give you a very short overview over some of the latest contributions that are very noteworthy. So starting with searches for charged lepton flavor violation at EP colliders. So this was done by the group around Stefan Antusch in Basel in the last year. Lepton flavor violation processes can be seen here in these two Feynman diagrams from effective vertices. So we have an electron in initial state. This blob denotes an effective vertex, and at the vertex it's converted into a lepton of a different flavor. That means a muon or a tau lepton. We have like a possible vector mediation here, or it could also be a scalar. And in their analysis, they considered the photon and the Z boson, and for the scalar, they considered the standard model Higgs. So this is model independent, and they get also limits on these vertices in a model independent way. And they carry out the analysis at the reconstructed level using this effective vertex and comparing it with backgrounds. So how does this work? Here on the top left, you see a small table that lists the dominating backgrounds for the tau lepton final state. And here on the upper right, you see the backgrounds they were considering for the muonic final state. You see the most important thing here is that the dominant background has a very small cross-section below a picobarn in both cases. And this is just for illustrative purposes. Excuse me. This is a distribution. There are many more, but this is the one I chose for you to see because it shows very clearly how the signal, which is shown here in blue, is well separable from the backgrounds. So the backgrounds tend to peak. So this is the angle of the muon candidate or lepton candidate. So this should be a muon. This is an error in the printout of the plot. So the background peaks or prefers very small scattering angles, which is not surprising because they're produced electroweakly. And those decay products tend to be produced in the forward direction following the proton beam. And the signal, however, is produced in the backwards direction, which is one of the major findings, which has come up in the past and it keeps being an interesting feature. So you can immediately see how easy it is to separate signal and background in this kind of situation. And I must say, usually this group employs boosted decision trees and neural networks to enhance signal over background sensitivity, but I didn't do this here. It was not necessary. So the sensitivity, which is shown here in these two plots, is cast in a model. As I said before, it was done or extracted in a model independent way, but I recast it in a specific model with stera and neutrinos where the flavor violation is proportional to some combination of mixing angles. And you can see here, and on top is the conversion of an electron into a muon. And the colorful lines are the existing constraints from low energy flavor experiments. And you can see black. The black line is the LHeC hypothetical reach. And you can see it can beat the current limits. I must say in the next couple of years, these limits will be improved, and it's unlikely that LHeC can compete with the improved limits unless something were to be found, which would be interesting by itself. But in this lower panel, if you see these two also existing limits, but they are very difficult, if not more or less impossible to improve. Maybe our friends in Dubna can do that, but it's difficult to do low energy physics of tau leptons. And so the LHeC has a few orders of magnitude improved reach compared to the low energy experiments, which would be the world leading reach in electron tau conversion limits that is foreseeable in the future. Now, there was a study that I've done in collaboration with some friends here. Jose Zurita is known maybe to some people here on exotic Higgs decays into displaced jets at the LHeC. So we considered a model with an additional scalar singlet that can couple and mix with the standard model Higgs field. And then we have two Higgses in Higgs mass eigenstates. The one is the would-be standard model like Higgs boson. The other one has a different mass that we take to be like order 10 GeV or so. Then the lighter Higgs-like or scalar boson can be produced in a decay chain from a scalar Higgs, from the Higgs-like boson with a small branching ratio. And typically it's a long-lived particle, so it has displaced decays, which is very difficult to find at the LHC, but we will show in this article here, or in this article, here that can be found very effectively at the LHeC. So this is the Feynman diagram that denotes the process. You produce a Higgs boson, or would be Higgs boson on shell, and it decays into 2 of the long-lived H2s, and they decay after some displacement X1 and delta X2 into 4 B jets. And we did an analysis at the considering the charged current Higgs production only. This is a little bit, this has the dominant production of the Higgs boson. So it's the dominant channel, but the other one might be a little bit easier. So this, in the sense, our experimentally speaking, so in the sense our results are conservative. We consider this decay chain H1 to 2H2 to 4Bs with 2 displaced vertices. As I said, the analysis was carried out at a reconstructed level. We've required at least 5 jets and reconstructed H2 candidates with displacement, that we didn't use any of the other kinematic handles that we have, so we can still improve our results a little bit. There's a point here. So at the reconstructed level, if you want to consider displacements, this is the way to go at the moment. That worked straightforward for us. And these are our results. On the left, you see a reach plot. On the horizontal axis, you see the mass of the light scalar H2, and on the vertical axis, you see the mixing angle of the Higgs boson squared. So if you are familiar with these numbers, then you know what it means. But if you're not, then let me say like this: for the LHeC, it's very difficult to get below 10 to the -3 values. Okay, and also lepton colliders can maybe go to 10 to the -5. And every collider prefers a different mass and lifetime and mixing regime. So let's not look at all these different colors, that will take too much time. So the bottom line is we can test very small masses. The best sensitivity is like 10 to 20 GeV. And in the mass range, and really small mixing angles can be tested in this way. And also in terms of branching ratios of the Higgs boson into the exotic branching ratios into 2 long-lived scalars can be tested for lifetimes between 10 to the -4 and 10 to the -1 meters. And I must also say here that the LHeC has some reach, but typically for like slightly heavier particles, 40 to 50 GeV maybe, so comparable to the orange line, and also for a slightly longer lifetime. So in a sense, there's a good complementarity here between PP and EP colliders.
And Oliver, you have 5 more minutes.
Okay, I think I'll make it. There's another work that we carried out testing the RD star anomaly at the LHeC. So to do this, we extended the standard model with a lepton quark that has an up and a down type component. It's called R2. The R2 component lepton quark can couple with Yukawa couplings. Let me skip the details with the standard model quarks and leptons. And it can be used, which we haven't done, but we took from the literature, to explain this RD star anomaly, which is defined by the ratio of B decays into taus and muons. So ratio of branching ratios, and this is found to be anomalous. One of the flavor anomalies that I've mentioned before. At the LHeC, these lepton quarks can be pair produced, and strong limits, especially on the 3rd generation searches, dileptons and jets plus met exist. And then there are also other limits coming from atomic parity violation, rare B meson decays, and others. So here's an updated parameter-space plot listing the mass of the lepton quark, and also the one of the couplings that's relevant for the 3rd generation on couplings. So we listed here all these colorful areas are current LHeC limits, and the red area is where we can explain the RD star anomaly, which is very interesting because we can have exactly this limit, and in this window we can have a parameter space that can be tested by the LHeC, and then we zoom on the mass of 800 GeV on this little plane here and extend it, because we actually have more than just one coupling constant, namely the one that couples to the 3rd generation and the other one that couples to the 1st generation. And this one will be relevant to produce it at LHeC. And you can see there's a sizable amount of parameter space left where we could produce it and test it. And a way to test this at the LHeC is to produce a lepton quark from electron and down quark type, call it a fusion or interactions on an SNS channel resonance. And the final state would be tau and B. There are others too that we did not consider. So also here we are kind of conservative. And also here for illustrative purposes is a kinematic distribution. So this is the invariant mass of the final states. And you can see the top, the lepton quark candidate mass is shown here in red. And it's very different from all the standard model backgrounds, which cluster as lower energies because they're weak processes. And we can find that for very small, for order 100% level Yukawa couplings, we can get a positive signal on this particular resonance. Then there's one more interesting article that was done by a group of Chinese people here on doubly charged Higgs bosons that we can produce also at EP colliders. So that means we extend the standard model with a SE2 left triplet scalar, which we call here delta. This is motivated from the neutrino masses. So forget all of this. I mean, it comes with Yukawa coupling and the VEF, and this dictates the details of the model. It's constrained by lepton flavor validating processes. There are also constraints from precision measurements, which limit also the VEF of the new the vacuum excitation value of the scalar triplet. And LHC searches are surprisingly inefficient as long as the doubly charged scalars are not decaying into dileptons that are of the same sign. And that's very interesting. You can also have a look at this article where we listed all the current constraints. So the authors of the Chinese authors considered double production of two scalars of which at least one has double charge and decays into two leptons. They consider in particular two same sign muons plus jets, and they evaluated the signal by analytical calculation and simulated with a Vegas Monte Carlo simulation tool. And the backgrounds were considered in MATGRAPH, I believe at a parton level, and this is basically the result. So the analysis can still be improved, but they find with that it's very difficult to test these particles at the LHeC or even at the FCC-eh because of the small production cross sections, even though the backgrounds, as I said, are very limited. There's also room for improvement in this study, but I won't go into more details. There are more interesting articles that came out or are to be coming out after our update paper was submitted to the archive. Here's work of Manimala Mitra and Al company on displaced neutrino jets at the LHeC, which will come out very soon. And then there are 4 more articles, which for the sake of time, I couldn't discuss in more detail. And here are already my conclusions. So the LHeC generates a lot of interest in the pheno community in the past and also at the moment. The driving factor is the complementarity to PP and EE colliders, which is more and more appreciated all over the place. There are many opportunities for beyond the standard model physics, in particular from physics that is hidden at the LHeC. And the reason why it's hidden could be, for instance, because it's long-lived. So there are displaced vertices which confuse the triggers at the LHeC. There could be lepton flavor violation, not only with the muon flavor, which is easy to see at the LHeC, but let's say electron and tau flavor related, which has some advantages, as I mentioned. If you have scalars that are not too heavy, but don't decay preferably into leptons, it's difficult to find them at the LHeC, but we can see them quite well at the LHeC. And also if we have bosons that are not particularly heavy, so on a few GeV scale, maybe 10 or so, then we have some advantages and there are more. And the last point I want to make is really important, not to forget that EP is really essential to exploit PP measurements because of the PDF measurements that we need to reduce the uncertainties, and also that we add significant to the Higgs and electric measurements. And that's already everything.
Thank you, Oliver, for this very enlightening and comprehensive talk and summary about the BSM activities. Are there questions to Oliver? Hubert, yes, please. You're still muted?
Yeah, okay. Hello, nice talk.
Thanks.
My question, is there any scenario or are there BSM scenarios for which you would need a positron beam?
Excellent question. So let me say it like this, if you have free choice of beam, I think the positron beam might actually be preferred, especially in the leptoquark scenario. This is something that we are seeing in this work, and it was found by Mitra and company before. If you have leptoquark scenarios, then you couple to a preferred, I forgot the details. I was actually anticipating the question, but I didn't look up the details. But if you take an electron beam, you have to take I think you have to merge with an anti-quark. And if you take a positron, you merge with a quark, and you have slightly larger PDF values for the quark currents. And at least I think that's what we found.
I understand you would reach different leptoquark states, of course.
Right, the production cross section is bigger, and also it doesn't drop off as quickly. So the PDFs actually really prefer the positron beam for the leptoquark scenario.
Okay.
And also one thing, sorry, I want to quickly elaborate on this because I didn't mention it at all. But also the possibility of having polarization is really useful. And this has not really been exploited or studied in great detail, but we also see there's some obvious differences in the background production cross sections, and also in some sense in the kinematics. But the signals often depend very differently on the beam polarization. So if you have good control over beam polarization and also electron versus positron, you can really fingerprint a hypothetical signal much better than let's say in PP collisions. You have much more control.
Okay, thank you.
Thanks.
Yeah, thank you, Oliver. Are there more questions to Oliver? I have one very subjective question. You make up always the both future experiments, LHeC and FCC-eh. What do you consider is more important, luminosity or center of mass energy?
I don't think you can answer. I mean, I think they're both. You have to maximize. I mean, from a BSM perspective, seeing that we don't have any clue where to look, you have to maximize both. But if you have, so the answer is very model dependent. I think in general, increasing them both has a similar positive effect, right? But in some cases, the beam energy is much more important, obviously, when the phase space is limited because the particles are simply too heavy to be produced, or it's the elliptic quark and it's slightly below the center of mass energy. Sorry, we are slightly above the center of mass energy in mass, so we can produce it on shell. So there's some obvious preference for the energy, but the luminosity always helps too. So, I mean, let me say it like this: if you have it running and you get a signal towards the end, like we have at HERA, let's say something that we're not completely sure, we should do both. We should increase the center of mass energy and do a longer dedicated run, and that we'll know for sure. And that's actually a positive statement, right? Because you can do it. You just need like one additional year with a dedicated running at slightly increased energy, and then you know better.
Yeah, I see. Thank you. More questions to Oliver? If this is not the case, so thank you, Oliver, once again for this very, very comprehensive talk. Thank you very much. And thank you all the speakers in this session. I think this was a very enlightening and interesting session, at least for me. The next session in our working group starts already in 8 minutes, so we can have a very short break for coffee, dinner, breakfast, whatever, in which time zone you are. So we have a break of 5 minutes now and meet again in 7 minutes, yes, depending on the time zone. Okay, thank you all.